Hi, in this video, we're going to look at distance vector routing operations from cold start to convergence. Okay, so distance vector. So, sometimes it used to be called routing by rumor. Some people used to call it that. But remember, distance vector, the router only knows what its neighbors tell it. So when a router first powers up, it knows nothing about the network topology. What it first knows is its own directly connected networks. And that's because you configure an IP address on an interface, and that tells it what network it belongs to. Similar like your host computer, right? When a computer has an IP address and subnet mask, or an IPv6 address and prefix, well, let's just stick with IPv4. IPv6 works a little differently. But an IPv4 address and subnet mask, it uses that to determine what network it belongs to. All right, so we look at router R1 here, and it has two directly connected networks. It says, okay, I belong to those two networks. R2 says I have those two directly connected networks. And R3 says I have these two directly connected networks. That's all it knows initially, each router. Okay, now the initial exchange of information. We're using RIP here to kind of explain how this works. Okay, so we'll be using hop count, which is just how many routers away is that network. Okay, there is something that's involved. We'll talk about it a little later called split horizon, but for now we're going to leave that out just to keep things simple. So router R1 advertises its networks, okay, that it's two directly connected networks out both of its interfaces. And we see that for the other two routers as well, R2 and R3. So what's happening here is each router knows about its own directly connected networks and then advertises that by the use of the routing protocol message, in this case RIP, to tell its neighboring router, says, hey, these are my networks, and you can get to them one hop away. That's that one. I mean, that's one hop for you to get there. Okay. All right. So if we take a look at one of these here, let's take a look at R2 telling R1 about the 10300 network one hop away. R1 says, thank you very much. I'll put that in there. The R stands for RIP. And to get there, it's one hop away through my serial 000 interface. R1 tells R2, says, hey, you can get to the 10100 network through me. And R2 adds that to its routing table. So it now knows it can get to the 10100 network via R1 one hop away. Okay, R3 tells R2, says, hey, you can get to the 10400 network through me. R2 adds that to its routing table. And remember, R2 is going to tell R3, hey, you can get to the 10200 network. It's directly connected network. We're assuming that's all it knows right now is it's directly connected networks, and tells R3. So this is kind of the first round of updates. Are we converged yet? Does everybody know about all networks? No. R2 knows about R1 and R3's remote networks, but R2 still has information to tell R1 about R3's network, and R2 needs to tell R3 about R1's network. Let's get there. Okay. So they, again, send out their routing information, and it really depends on the routing protocol how this is done and when it's done. But just to keep things simple here, we're going to have R2 tell R1 about the 10400 network, okay, which it has in its routing table. It says, I'm one hop away, which means it's going to be two hops for you. One hop through me, and then the next hop through R3. So R1 adds that to its routing table. It says, okay, 10400 is two hops away for me. Okay. R3 is also going to tell R2 is also going to tell R3 about the R1's 10100 network, which is one hop for R2, but for R3, it's going to be a second hop because it has to go through R2 to get there. And R3 adds that to its routing table. Okay, at this point, we are converged. All the routers have full, complete, accurate knowledge of the topology of the routing domain. Okay, I mentioned split horizon. Split horizon is rule states that a router should not advertise a network through the interface from which the update came. For example, R1 learned about the 10300 network and 10400 network from R2. So R1 is not going to tell R2 about that network. It says, no, you told me, so I'm not going to tell you. You're the source of my information. So I don't want you to think I can get there, because the way I get there is through you. So this is to help prevent routing loops caused by slow convergence. Now there's another feature of this called split horizon with poison reverse. And this concept of split horizon states that it's better to explicitly tell another router to ignore a route that's better than not telling it about it at all. So with poison reverse, R1 is going to tell R2, hey, the 10300 and 10400 networks, I'm telling you explicitly you can't get there through me because you're my way there. So don't think you can get there through me. Okay. And that's where that 16 is actually in RIP, the maximum hop count. It's unreachable. 15 is the maximum number of hops, and 16 is known as unreachable or infinity in RIP. Okay, route poisoning, similar in RIP, it's used to mark a route as unreachable. It just poisons the route. It says when a route is down, it is sent as unreachable. In RIP, it says 16 hops. R2 says, oh, 16 hops, that's too far. That means I can't get there through you. It's unreachable. Okay. All right, so that's distance vector routing operations. Yeah, and you'll learn more about distance vector routing protocols, especially when we look at EIGRP.